Hi everyone, I'm Wenlei from Meta. I'm very happy to be here in the beautiful city of Vienna to share our work on how do we improve sampling-based PGO in LLVM with context sensitivity and pseudo-instrumentation. So this is the agenda for my talk today. First, I will quickly go over our motivations, then followed by PGO architecture overview, which would review some of the challenges of existing PGO in LLVM. Then I will talk about the two main contributions of our work, which is pseudo-instrumentation and context-sensitive PGO, sample PGO. Last, I will share some results for CSSPGO in Meta's production data center workloads. Okay, so PGO today often delivers double-digit percent CPU performance improvement for applications. Now that combined with the sheer size of data center makes a really attractive tool for optimizing data center workloads. However, we got a problem. We have a tension between the operational overhead at scale and the best peak performance. We have different PGO technology in LLVM that occupies different ends of the spectrum. On one end, we have auto FDO, which is really low overhead, but it lags behind in terms of performance comparing to instrumentation PGO by a couple percent. Instrumentation PGO, on the other hand, it delivers the best peak performance, but it is really high overhead because it requires instrumentation, it slows down your training, so you need a special training tier setup for data center usage, which makes it less scalable. We're faced with a decision that we're not satisfied with. So we ask ourselves, how do we get the best of both? In order to answer that questions, we look at what are the things that can affect the performance of PGO. It comes down to profile quality and the optimization. Now, if we actually compare instrumentation PGO with sampling PGO, we can see that they largely share the same optimization pipeline. And even most part of the PGO infrastructure, for example, the BPI and BFI stuff in LLVM. So the key difference in performance really comes from the profile quality difference between instrumentation PGO and the sampling PGO. We talked about how instrumentation slows down training, which makes it difficult to scale for data center applications. So we turn the question of how do we get the best of both into how do we improve profile quality for sampling-based PGO. In order to improve profile quality, first let's look at what are the things that actually cause profile quality to degrade. Let's start with a traditional compilation pipeline. We have source code going through a bunch of optimizations, and at the very end, we generate a fully optimized binary. Now, if we apply PGO on top of that, we would then get a profile on the fully optimized binary. In order for that profile to be consumable by the compiler, again, for PGO, we need to map that profile back to a profile on an optimized IR. This is a process we call profile correlation. Once we get the profile on the optimized IR, it is used to drive the next round of PGO compilation. Now, in this case, each optimization is both a consumer and a producer for a profile, because it needs to adjust the profile based on its own transformation so that the next optimization pass can still see an accurate profile. This is what we call profile maintenance. Our investigation found out that profile correlation and the profile maintenance for inlining in particular are the biggest source of profile quality degradation. And this is also where we focus our effort on. Let's talk about profile correlation first. So this is about mapping profile on fully optimized binary back to profile on an optimized IR. The key of that is to have a set of really reliable correlation anchors. Now let's compare the profile correlation anchors of existing PGO and see how we can improve upon that. Start with auto FDO. This is the sampling-based PGO implementation in LLVM. It uses debug information as the correlation anchor. The obvious benefit is that it has zero overhead, because generate debug information doesn't slow anything down. But we all know that debugging fully optimized code sometimes can be challenging because debug information from fully optimized code isn't that reliable. That same challenge also applies to correlation. For that reason, LLVM sometimes doesn't have the best correlation quality. On the other hand, we have instrumentation PGO. Here we use intrinsics to serve as the IR anchor. These anchors may block some optimization, but the overhead from that particular anchor in IR is minimum. Now, when they get lower into actual counter increment instructions at runtime, this really just kills performance. So the benefit of instrumentation PGO is that you track execution counts very accurately and you have great correlation, but it's not scalable because the performance overhead is very high. You cannot just run this in production. We propose something that's sitting in between the two. We call it pseudo-instrumentation. Like instrumentation PGO, we have intrinsics as the IR anchor. This may block some optimization, but it's tunable and you can tune it based on whether you want the best profile quality or the lowest overhead. Unlike instrumentation PGO, these intrinsics, they don't get lowered into any real instructions. Instead, they materialize as some extra metadata to help with correlation. So this avoids the runtime overhead from the counter increments of instrumentation PGO, but try to preserve some of the benefit of instrumentation PGO. Now, as I just mentioned, this is tunable. We can make the semantic of pseudo-probe intrinsic strong or weak depending on what we need. In our implementation, we choose a weak implementation so that the overhead of pseudo-instrumentation is kept at minimum. We just assign some memory semantics so that these intrinsics don't get randomly moved around or be removed arbitrarily by optimizer. This table shows the result in terms of correlation quality and overhead comparing the three correlation technology. As we can see, pseudo-instrumentation still has near zero overhead for our implementation, but at the same time, if we use instrumentation PGO as the ground truth, pseudo-instrumentation still achieves noticeably better profile quality comparing to LLVM. After profile correlation, the next big challenge for profile quality is the post-inline profile quality, or the profile maintenance for inlining. Let's look at a contrived example to show the problem first. Say we have two functions calling into scalar add and scalar sub going through some dispatch function. Now, if we don't have context-sensitive profile, we would end up with something like this. After inlining, you lose the context profile, so the counts are just scaled and inaccurate. However, if we have context-sensitive profile, after inlining, we would be able to retain the accurate profile based on your calling context or the inline stack. The conventional way of getting a context-sensitive profile or having better post-inline profile quality is just to do another round of profiling, either through post-link optimizer like BOLT or through in LLVM, there is a two-stage instrumentation PGO implementation called CSSPGO. But these things, it's not easy to operate at data center scale because you now need another round of synchronized profiling. Alternatively, we propose something that's lightweighted based on the existing sampling profiling technology to obtain the context-sensitive profile. So we extend traditional LLVM sampling. With traditional LLVM sampling, we get 32 or 16 pair of taken branches from the Intel PMU support. And now from these taken branches, we can derive linear execution ranges. And these can be turned into a compiler PGO consumable profile. Now, if on top of that, we also take synchronized stack samples, we would then be able to use the stack sample to identify the calling context for the leaf branch of the LLVM. And we can also replay the LLVM branch backwards on top of the stack sample to recover the calling context for any branches and ranges within the LLVM. Say if we encounter a call in the LLVM, we would then just pop a frame from the stack sample, and the adjusted stack sample can be used to identify the calling context for branches before the call in the LLVM. This is something that we call virtual unwinding. With all that, still for the contrived example from the previous slides, Instead of having a single profile for scalar add, now we would have two profiles for scalar add, depending on the calling context. And all of this is done within a single round of profiling. So getting context-sensitive profile is the first step, but it's not enough. We also need a cooperative inliner to take advantage of that. Specifically, we want the inliner to be able to do specialization based on context. This is useful for both post-inline profile quality and also for better inline decision. With LLVM, the main inliner, CGS-CC inliner, is a bottom inliner, so we cannot really do specialization there. We introduced a top-down inliner in the sample loader to achieve that. There's another problem that we need to solve, which is about merging not inlined context profile back into the base profile. Still with this example, say if the inliner decided we're not going to inline scalar op anywhere, then we need to merge the context profile back to its base profile. This is usually okay, but if scalar op is in a different module, and if we're using SynLTO, then we got a problem because we cannot easily transfer the profile counts from one SYN backend to the other end, the other SYN backend, given that they can be running in parallel and all on different build hosts. So we mitigate this problem by introducing a global pre-inliner, which actually runs during profile generation. It uses the profile hotness and the binary function size from the previous build to estimate the inline decision and then pre-adjust the profile across different modules. Okay, so let's now zoom out a little bit and then look at the summary comparison between the inlining strategy between AutoFDO and then CSSPGO. For existing AutoFDO, we want the inlining to be driven by profile. So we have CGS-CC inliner, which is main inliner that does that, but it doesn't support specialization. We want to preserve some context that's carried from previous inlining. So we have an early replay inliner that does that. For CSSPGO, we want the inline decision to be driven by profile, and we also want the inliner to be able to do specialization. We have a new top-down early inliner that takes care of that. And as we just talked about, we have a pre-inliner that takes care of the problem of merging profile across different modules. And of course, we still have the CGS-CC inliner that takes care of the rest of inlining. Okay, so far we talked about pseudo-instrumentation, we talked about context-sensitive sample profiling, and also context-sensitive inlining. Now, if we put everything together, we have an improved sampling-based PGO system, which we call CSSPGO. You can find more information about our work in the CGO paper for this year, and most of the implementation is in LLVM upstream already. Also, CSSPGO has been used in Meta for production for some time now across the 21 global data center regions. The table below shows compiler PGO breakdown by Meta's fleet CPU cycles. As we can see, the majority of the cycles are actually being optimized by CSSPGO now. Next, we will take a few top services from each segment and then do a performance comparison to see how CSSPGO works in production. So this chart shows the performance comparison for the top 5 services in Meta's server fleet. We can see that CSSPGO delivers about 1 to 5% additional performance on top of AutoFDO. And in the case of HHVM, we also have instrumentation PGO data. In this case, CSSPGO is able to deliver about 60% of the extra performance of instrumentation PGO. For other workload, we don't have instrumentation PGO data because it's just running too slow and we cannot reliably get instrumentation PGO to work. It's also worth mentioning that CSSPGO delivered performance while reducing the code size. We emphasize a lot on the importance of low overhead for data center usage of PGO. Now, this chart shows that with our implementation of pseudo-instrumentation, the overhead is actually near 0, and that makes it really scalable. the chart on the right shows that for the metadata of pseudo-instrumentation, the size is also reasonable. It's smaller than the debug information. The low runtime overhead and manageable size overhead make it possible for us to kind of hide this CSSPGO thing in the background. So we turn this on by default. We turn pseudo-instrumentation on by default for all the data center applications running for Meta. Great. So this is all the main stuff that I have for today's talk. It's good that after spending with my kids for the spring break and skiing the Alps, I still remember what I need to talk about. So I may go off rail here a little bit. Okay, skim through the recap. So we introduced CSSPGO, and we show that CSSPGO can deliver about 1 to 5% performance on top of AutoFDO for Meta's data center workloads. I'd also like to share some thoughts on PGO and its evolution in LLVM. So for many compilers, PGO felt like a bolt-on piece. And it's understandable because, say, when designing a new compiler, usually people don't think about PGO as one of the essential feature set, because we want correctness and some of the textbook style optimization to be right and in place. But as compiler matures, now PGO has become an increasingly important and powerful tool in squeezing out the last bit of performance. And this is also evident by the number of PGO talks we have today. And we will have another talk from my colleague Alex about how do we use PGO to kind of take care of performance size in the mobile world. But there's kind of a gap between this bolt-on piece and the need for it. So I think we, Meta, and together with the community, we're trying to turn this bolt-on piece into a first-class citizen in a compiler, in this case in LLVM. We have some thoughts on the aspirational challenges. For example, if PGO is perfect, now if the whole cycle is perfect, at the end of compilation, if we just get counts for each basic block from MBI5, we should have something that tracks the actual dynamic instruction count of the program pretty closely. But unfortunately, that's not the case. And there are a few other examples where we kind of lag behind comparing to the ideal state. We have some thoughts on what we can do to improve things, like tightening up profile maintenance and also shifting more inlining from the main CGSCC inliner to a more PGO-friendly inliner, be it top-down inliner we added, or maybe something like the modular inliner. I think there's also a need for some infrastructure or even verifier style things in LLVM to make sure that profile maintenance in the compiler is actually future-proof. Because we can keep fixing things, but if there's no scaffolding or guardrail, it's probably not sustainable. So we believe that PGO hasn't realized its full potential in LLVM yet, and the team at Meta is working on that, and we are very happy to collaborate with everyone in the community to keep improving for PGO. That's it for my talk today. And
all right, let's thank our speaker. Are there any questions? You go.
Do you have an estimate for how you said this extra function calls, the bogus function calls you introduced, was also hampering some optimizations? Do you have an estimate of how much percentage you lose by adding those?
You mean the overhead of pseudo-instrumentation?
Yes.
So we run it on our very large data center workloads. And actually, this is the number that we got from the real production. There may be some overhead, but the performance measurement is also challenging. So what we observe is this is barely breaking the noise barrier for our measurement. So it's pretty low. I think it's maybe around 0.2% or something like that.
Okay, more questions? One thing I was wondering is, you mentioned you also save quite a bit of code size. Could you share some of your insights why that is happening?
Yeah, so we did some analysis, and evidence are pointing to more effective inlining. So while we want the top-down inliner to help with profile quality, but it is also a intended effect that it will help with more targeted and selected inlining. So that's the reason for code size reduction.
Thank you. And more questions, please go ahead.
Hi, Wenlei. Thank you for your talk. It's very interesting and has a great impact on the industry and our internal workloads. So I have a couple of questions and clarifications. First is, so CSSPGO improves on top of AutoFDO, but Bolt can also be applied on top of either. And how effective is Bolt on top of CSSPGO, and whether the combined effect is higher with CSSPGO over AutoFDO. So that's first thing. The second thing is when you mentioned the overhead of pseudo-probe metadata, you've compared it to debug information. What kind of debug information is that? Is that just one section, debug line, or the total? And the final thing is, okay, let's keep it short.
Okay, yeah, so that I can remember all the questions. So for first one, thanks for the question, Amir, by the way. It's actually a very good question. There is indeed a little bit of overlap between compiler PGO and then PostLink optimizer in general, but I'd say that from our experience, combined together, we still get meaningfully better performance. Practically for the workloads that we measured, Bolt and CSSPGO overlap about half of the win that we get from CSSPGO. This is just because, as profile quality improves, compiler would also do a better job at doing code layout, which is the thing that Bolt does really well. But there's also part of better inlining and also better register allocation. These things are dependent on better post-inline profile quality. Now, compiler improves that, and that doesn't overlap with both. Hope that answers the questions. What was the second question? So what specifically about the metadata?
Compared to debug information.
Okay, so we use G2, which is the standard debug information. It's a little bit more than G-debug lines. And also, it's worth noting that we didn't completely get rid of debug information because you need that anyway for like visualization or debugging purpose. This is not to say that we have pseudo-probe, which makes the binary smaller, but it's just the binary size overhead is quite manageable.
Okay, let's take one more question.
Yeah. For the CSSPGO, it's based on the LBR. So if the architecture don't have LBR like the ARM, we don't have the LBR or don't have the BRB. So what's the performance we can get from the other architecture? This is the first question. And the second is that, so for the stack frame sampling, I think it must be enabled the frame pointer options. If we add the emitter frame pointer, so it can still work.
Yeah. Okay. So for ARM, we don't know because we still today most of the workloads are running on x86 architecture. But it's a good question. It's something that we need to deal with, I guess, for the entire industry. Either the hardware vendor come up with something that's sort of equivalent to LBR, which I think ARM and AMD both have their kind of recipe for that, or we come up with something from the hardware side trying to emulate that. I think Google has a paper on that, which is quite interesting. And the other alternative is we just get the profile from the x86 binary and then see how it use that to optimize the ARM binary and then see how it works. Yeah.
Okay. I think more questions you can have in the hallway. So let's thank you, Wenlei, for the talk.